Hey everyone, in this video we're going to get a commercial grade sensor like this laser photoelectric sensor where voltages are typically 12 or 24 volts, step it down to 3 volts so this microcontroller can detect it, and then we're going to get the microcontroller to play a message over a Google Home speaker.
Laser sensor has been triggered.
So if you're not used to using commercial sensors, you're really missing out. They get the job done much better than these little hobbyist Arduino level sensors. So this one here I got off AliExpress. This isn't a paid promotion or anything. The reason why I bought it is because it's cheap. This cost about 25 bucks landed, whereas usually these commercial grade sensors, specifically this style, photoelectric, can cost $150 at the cheap end and go up as much as $400. So I thought I'd give this a shot and see how it behaves and if it's worth the money, 25 bucks. Now this one is a laser photoelectric retroreflective sensor, which means that it has a onboard laser. It fires a visible wavelength red laser light to this this retroreflector, where it bounces back and gets received on the sensor. So if it detects the laser beam broken, then it will trigger an output voltage. Now, once you get into the commercial grade, and there's a little bit more technical stuff you do need to keep in mind. They have a onboard transistor. This one is an NPN. So that means it's if you supply a positive voltage to the sensor, it will close a negative circuit. It's also NO, which is normally open. So you can buy these in any combination. You can get them PNP or NO or NC, normally closed sensor. So I just happen to get this one. It's got an internal transistor which is NPN, and it's also normally open. So what happens is, with this, if the sensor gets broken, it will output the input voltage as a signal. It's also got a little calibration on there. It's meant to do 8 meters if you have a look. So it's pretty impressive specs for this type of sensor. And if you look at their packaging, it's pretty cool. It's got an industrial look to it. You can see that it will accept a voltage input of 10 to 30 volts DC. So any of that voltage. So here's the other end of this sensor. It's got 3 wires. All you need to do is provide it a voltage feed between 10 and 30 volts, and it will output that as a signal whether the sensor gets triggered or not. And it's also pretty cool because it shows you the basic schematics on this sticker here. So without knowing Chinese, they've got the schematic with the NPN, normally open. So BN, I'm assuming, is brown. If we look here, that's our positive voltage line. Then we have our negative is BU, which is blue, so that's our negative. And then this sensor output is the black wire. That's the little switch. So let's set it up and I'll give you a quick demo of it working. So I've turned the light off so you can see the little laser a bit more visibly. It includes this little reflector. So if I break this reflection, this laser, boom, you'll see the sensor's triggered. It's even got a little LED indicator on the back. There you go. And this is meant to work up to 8 meters, which is pretty impressive. So for this project, I'm going to power it with a hard drive 12 volt plug. I've got a little breadboard that we're going to assemble this together with. I've got this little adapter that takes a 12 volt input, and it's got 2 regulators at the top where you can choose 3 volts or 5 volts. So basically I've said let's have 3 volts down this rail here, so we'll use the 3 volts here. Now what it doesn't have is a 12 volt output, so I've just soldered a little jumper pin directly to the output of the 12 volts here, and I'm just going to plug it anywhere and we will get 12 volts here. So we'll use that for our sensor. We're just going to marry up this brown with this brown. And blue will be our negative. So if you can just see the red here, that's our positive 3 volts. We're going to use the common ground, which is the right column. Alright, stick those in there. Now if we power that up, this laser should work. So the black wire coming out of this sensor is our signal wire. It outputs a 12 volt signal, and we need to use that with our microcontroller. The problem is, with most modern microcontrollers, and the one I'm going to use is a ESP8266, is that they have a 3.3 voltage logic signal. So if I put the 12 volts into this microcontroller with the 3.3 volts, it will damage it. So we need to convert this 12 volts down to 3.3 volts. Now you'd probably think, well, that's easy. Why not just use another voltage regulator like the 1117? So this one can have a voltage range anywhere from 10 to 30 volts and output 3.3 volts. The challenge is that with most digital circuits, this 12 volts is actually a quiescent current. So it's a very low amperage current. And it's below the rate that this voltage regulator needs to be able to output 3.3. So we need another solution. So for this, I'm going to use one of these little things. And this is a optocoupler. So the idea is that we're going to put the 12 volts on this side, and we're going to have a 3.3 volt circuit on the other side to power the digital input logic of the microcontroller. Now the most common optocoupler you'll see out there is the PC817. That's fine. It's just that my little local parts supplier has this, and this one is a 4N28. So the idea is that there's a little infrared LED inside this, and when it gets current, it'll turn on the other circuit. It's that simple. Now, if you're new to using a breadboard, you will need to put this chip in the middle to isolate each side. So this will separate it. Now let's look at the pinout for this chip. We've got pinout 1 at the top. That's our input for the LED, and pin 2 is our output. This one, pin 3, has no connection. It's not used. Now the other side, we've also got a pin here. This is our base. We're not going to use that. We don't need that. We're going to use the collector for our 3.3 volts, and the emitter is the output. Now before we go jamming our 12 volt circuit into the input, let's take a look at the data sheet and see what we actually have to input. If we take a look at our data sheet, it's got the input forward voltage, which is 50 milliamps at 1.3 volts. So we need to feed 1.3 volts in, not the 12. We have to put a resistor in front of this optocoupler. And to figure out which resistance value we need Ohm's law. Resistance equals voltage over current. So we know the input voltage is 12 volts, and we need to subtract the 1.3 volts for the optocoupler. Then we divide it by the current. Now that's the current of the optocoupler, which is 0.05 amps. If we do the maths there, 12 minus 1.3, that gives us 10.7 volts divided by 0.05 amps, and we will get a value of 214 ohms. Now, they aren't going to make the exact value in the resistors. We just need to find the one that is the closest. If I dig through all my resistors, the closest I can get is 220 ohms. That'll be fine. We'll use one of them. So if we put our 220 ohm resistor before the input pin, and we'll go up another level. So we're on row 8. We'll go to row 7. We'll put our input to the resistor. We should now be getting our 1.3 volt. We'll need a wire to ground. Let's use this black one. So remember, that will be the next pin down, pin 2. That'll go to ground. Let's power it on and see what we get. So let's measure with our multimeter. We'll probe the ground and I'll probe the input. And look at that, 1.29 volts. Bang on the requirement of 1.3. So now we just need to connect the right side of this optocoupler to our 3.3 volt circuit. So if you remember, this pin here, pin number 5, is our collector. That'll be our input. And we've got the 3.3 volts from this regulator, a bit hidden up here, and it's coming down this rail on the left hand side. So I might just move this ground up a bit out of the way. And if we go to this side here, that's our 3.3 volts. Now that will be our input pin here. To see if this circuit works, I'll connect it to an LED and demonstrate this working. So this is a little red LED. 3.3 volts is safe to power it. Remember, the long side is the anode, that's the input in layman's terms, so that'll be the output of our optocoupler. And all we need to do now is give the LED a ground back over to this side. And it's a bit hard to see, but that's on. So if we manually turn the optocoupler on by disconnecting the 12 volts, boom, you can see that this complete isolated 3.3 volt circuit on the right is being switched on and off by the 12 volt circuit on the left. So the only thing left to do now is to use the 3.3 volt output, which is safe for our microcontroller, to trigger a digital pin. Let's program up the microcontroller. So let's have a look at the code that we need to write to program this microcontroller. So I'm just using the Arduino IDE with our generic ESP8266 board, and we're going to set our constants for our pins. So we're going to have the sensor input pin. This is pin number 4, or it's known as D2 on our development board. Okay, so that's a general purpose input output pin, and we're going to assign it to be an input for the sensor. Now, to see if we're getting any feedback from the sensor, we're going to assign the onboard LED that's on this development board. We're going to call it LED pin, and that is number 2. Now, pin mode sensor input equals input. Pin mode LED input equals output. So we want to output the LED on or off. Now in our void loop section, we're going to define the sensor state and its digital read the sensor input pin. So we're going to read the pin that the sensor is connected to, and we're going to figure out if it's low or if it's high. So if it's low, it'll have no voltage, and if it's high, it'll be reading the 3.3 volts that we feed into it. And based on this, we're going to turn the LED on, or high, or the LED off, which is low. So we'll program this little board, and we'll test it out. Okay, so the first thing we need to do with this microcontroller board is connect the power. You can see down here we got the 3 volts to power it and G for ground. So I will use a red wire for the 3 volts. And that just plugs in down here. This is our 3 volt rail on this side. We need the black wire for ground, and it should turn on. Okay, now remember we programmed D2, which is a general purpose input-output pin. That's where we're going to connect our sensor. But we're just going to hook this up in an isolated manner first and see if it actually works. You can see the LED's already kind of turning on and off without anything connected. Now that's a trick for newbies. We will need to add a pull-down resistor. So here's our D2 wire. Just going to plug it to here. And because these digital pins are floating gate, they're kind of really not in an on or off position. They actually need a resistor that pulls them down to ground or up to high voltage. So the most common resistor for this is a 10,000 kilo ohm, and I literally have one of these labeled ready to go for all these projects. So we need to pull this input pin. You can see that the LED is kind of unstable without it. It's kind of turning on and off because of that floating pin. So once we pull this down to ground, connect it up, and we'll plug this into... So that's going to make this more stable. Alright, we're not getting that kind of awkward on and off flashing yet. So now, the way we've programmed this circuit is that the onboard LED here will turn on and off whether we give it a 3.3 volt current or not. So let's just use this little orange wire. That's all connected to our D2 input pin. And we should be able to flash this on and off now. If I just connect this to our 3.3 volt rail down here, will do. There you go. So it's got 3 volts, the LED's on, off, and on. So that's working perfectly now with that pull down resistor. So it pulls it down to ground. Okay, perfect. It's working 100%. So now all we need to do is use our 3 volts that is coming from our sensor to turn the LED on or off. Let's try that. Okay, so the LED's on. Let's see if we can trigger the sensor to flash the LED. Okay, so I've got the laser sensor pointing directly at the retroreflector. What I want you to do is keep an eye on the blue LED when I break the laser beam. We'll use this white cardboard so you can see. And my hand. You can see as soon as the laser breaks, the LED's off. And it's working perfectly. And it's quite responsive, it's quite fast. So it's working fine. Now there's one thing we need to keep in mind here with this sensor. It's a normally open sensor, NO, which means that it's actually running the 3 volts now, or it's literally running an output signal of 12 volts, which we've converted to 3, when the sensor is open. I think this is called normally open. So basically, it's high when the laser beam isn't obstructed, and it's low when it's obstructed. So we got to make sure we're mindful of that in the code. So when it goes low, that means that the laser beam has been broken. I probably should have bought a normally closed one, but it doesn't really matter. It's just either or, high or low, as long as we know. So once we know that the sensor is low, the next thing to do is program to send a message to our Google speaker, as I promised at the start. Let's have a look at the code for that. So now we're going to update our Arduino code to reflect the ability to connect to the Wi-Fi and send a message to our Google Home Nest speaker. So if you have a look here, we're including the Wi-Fi library to connect to the Wi-Fi, and then we're going to use the PubSub client library. This is the publish subscribe client, and this is the MQTT protocol. So I'm not going to explain in detail what the MQTT protocol is if you're new to it or haven't heard of it, but basically it stands for Message Queuing Telemetry Transport. And it's a very simple protocol that lots of these little IoT devices use to communicate with each other. It's kind of like having a very small Twitter where they can send messages to each other and communicate. So it's very popular in the home automation scene and all these IoT microcontrollers. So in the code, we've still got our pin assignment for our sensor input, D2, our LED, which is the onboard, pin number 2. Now we need to set up our Wi-Fi credentials, which is the SSID and password, so that this board can find the Wi-Fi network and connect to it. And then we have our MQTT broker details. So basically, this will be an MQTT client, and it needs to connect to a MQTT broker. That's like the server for this. So it wants to know the address, it wants to know the port, and it also needs a user credentials and a name. So username, password to log on to this MQTT broker. And also we need to know what the message topic is. So basically this would be like a hashtag in Twitter. Simply it's the topic name for this protocol. We're just going to call it sensor/laser/1. So that's where it's going to send the message to. It could be anything. We could call it whatever we want. We could have it sensor/1, sensor/ this is a laser. So I've just named that myself. As long as we know the name, where the message is, kind of like the hashtag on Twitter, we'll find the message. Okay, so here I've got some functions for adding a delay that's non-blocking. I'll get back to that in a second. But the void setup, what we're going to do here is first we're going to start the Wi-Fi and try and connect to the Wi-Fi. I've got a function at the bottom that has all the Wi-Fi error codes, so it can print if there's a problem connecting to the Wi-Fi. Also, while it's trying to connect, we're just going to blink the LED on and off while it's trying to connect. Once it's connecting, we're just going to print a debug statement that we've connected. Now that we're connected to Wi-Fi, we're going to try and connect to the MQTT broker. Again, we're just going to blink the LED so we know that it's trying to connect, or if it can't connect, we'll see the LED on board blinking. Okay, now we're in our main code. So there's nothing very complicated with this code to handle the sensor input. All we're looking for is if the digital pin gets pulled to low, then we know that the laser has been triggered. So we're just going to write a little string message here, laser sensor has been triggered. We're going to print that to our debugging console here, just so we can keep track of it. And then we're going to publish a message to the MQTT service. So client.publish the MQTT topic, which is what we saw earlier, sensor laser 1, and then the message, which is the laser sensor has been triggered. So we're going to publish an MQTT message to the topic with laser sensor has been triggered, and we're simply going to turn the LED on and off again when that's happened. Now the only other thing here for this code is we need to just handle some rate limiting, otherwise it's going to spam hundreds of these per second. So we do have a bit of a rate limit of 2 seconds with this delay, but we want to make the delay longer, so I've added another 13 seconds down here. So this local delay, it's a little bit complicated, but basically I can't use the delay routine because that'll block all the code, and I found that it kind of interferes with the MQTT library. It kind of blocks the execution of code. So to get around that, I'm using this custom delay, which we call here, which was back up the top, this non-blocking delay. Now, I'm not going to go into super detail here. It's not that important, but instead we're just going to be running the millisecond kind of routine. And all this is just a timer. It's just going to time how long it's been, which we're going to count 13 seconds. This way, code can still execute while we're timing. If I was to use a delay, it will block this MQTT code from executing. We don't want that happening. So this is just a non-blocking way to have this C code on the with the Arduino continue to function without it being blocked with the delay routine, which does block the execution of code. And it's really that simple. So just a bit below, we've got a couple of other functions. I just have all my Wi-Fi statuses, so if there's something wrong connecting to the Wi-Fi, it'll just print out a user-friendly message like Wi-Fi is in the process of changing between statuses, unable to find the network with the SSID. So it's got all our debugging messages. Same again with our MQTT. We're just going by their statuses, and we're just going to print out user-friendly debugging information. Password's wrong, can't connect, can't find it, all that stuff. So very simple code. Now we'll program it to our little microcontroller, and let's turn it on and see if the complete setup works now. I should also mention how I'm going to handle sending the message to the Google Home speaker. There's many ways to do this. This is just the technology I use. Basically Node-RED. It's also an automation software. I love it. It's very simple. You can program it in JavaScript. And it just runs nodes, and we can link different nodes together. So without going into detail how this works, there's many ways you can pull this off. This is just an example that I use. We're going to have one node that can connect to the MQTT broker, and we just have to tell it the topic where to listen. Remember that? Sensor/laser/1. So as long as we tell it to listen to that topic, any messages that come to that topic, we're going to send to our Google speaker here. And that's how we're going to get the Google speaker to play that message. Here's our final setup. We've got on the left here, there's our laser sensor. Up on the wall here is the retroreflector. Then we've got the Google Home speaker that we're going to play the message to. And down here we've got the microcontroller and the electronics to power it. So let's plug it in and see what happens. Remember, we should see a flashing blue light. Okay, there's the flashing blue light as it connects to Wi-Fi and the MQTT system, and it's finished, so we know we're ready to go. Let's see if we can trigger the sensor now and get it to play a message.
Laser sensor has been triggered.
So I'll do it again. This time I've darkened the room a bit to make it a little bit more obvious. If you have a look just carefully at the retroreflector, you can see the little red laser dot reflecting back. So when the sensor gets triggered, you will see the blue LED turn on the microcontroller. So that's a successful detection. And the speaker will play our message. Let's have another shot.
Laser sensor has been triggered.
And there's a laser on me, and we can stand in here. Remember, we put the rate limiting of about 13 seconds, so it won't get spammed. I hope you guys liked that video. If you've got any other ideas we could try with this little sensor, leave me a comment. If you want the code or anything, let me know. I guess I can post it if anyone's interested in reproducing this. Remember, this sensor is meant to go up to 8 meters of distance, so we could probably test and play around with that, especially at day and night time. So I'll see you guys in the next video.